If someone says to you, "If I can't get a loan, then I won't buy a car," are they telling you the truth or are they lying to you? Well, there's a way to figure this out, and we can do it with symbolic logic. So if we let the simple statements, "I get a loan" and "I buy a car" be represented by P and Q, we can write a symbolic statement that means the same thing as our sentence. So what we'll do is make a truth table for the statement, "If not P, then not Q." Now when we do that, the important thing to look at is the last column in the table. That's called the solutions column. And it tells us under what conditions our statement is true or false. And what we can see is that there's one time when our statement is false. And that's when P is false and Q is true. So what that means is the lie is being told if we don't get a loan, but we do go ahead and buy a car. When we think about statements, we can classify them according to what we see as the truth or the falsity of the statement. If we are looking at a statement that is always true, then we call it a tautology. And if we look at a statement that is always false, we call it a self-contradiction. Now the example we just saw was not always true or always false. It had a mixture of truth and falsity. So it would not be considered a tautology or a self-contradiction. It's neither of those. So let's think about this sentence. If I went to the store and bought milk, then I bought milk. Let's see if we can convert that to symbolism to determine if it's always true, always false, or some mixture of true and false. We'll let P represent I went to the store, and Q represent I bought milk. So our sentence can be written symbolically as if P and Q, then Q. Now we need to make a truth table for this. So we'll need a column for P and Q, and we'll need a column for our entire statement, if P and Q, then Q. Once we complete the truth table, we can see that the solutions column is always true. Because the last column is all true, that means we have a tautology. In other words, it doesn't matter whether we went to the store or we didn't. It doesn't matter whether we bought milk or we didn't. The statement, "If I went to the store and bought milk, then I bought milk," is a true statement. Now let's look at this statement and see if it's always true, always false, or some mixture of the two. We'll need to make a truth table for it, and once we do that, we'll be able to determine by looking at the last column, the solutions column, whether the statement is always true, always false, or a mixture. And in this case, we have a statement that's always false. So we have what's called a self-contradiction. It doesn't matter whether P is true or Q is true, or P is false or Q is false. The statement itself is always false. Now what we've done so far is just look at the truth or falsity of a single statement to see if we can classify that statement. Now what we're going to do is compare two statements. The two statements we're going to look at are if P then not Q, and if Q then not P. So to make the comparison, we'll just make a truth table for each of the statements, and then we'll look at the solutions column for both statements. In this case, we have a perfect match between the two columns. False, true, true, true. If that's what you see, if the truth columns are identical for the two statements, then you have two statements that are considered to be logically equivalent to each other. Let's try comparing these two. P and not Q compared to not P or Q. Once again, we'll make truth tables for each statement, and then we'll compare the solutions column for the two statements. Now what we notice is that the solutions columns are exactly opposite each other. Where I see false in the first statement, I see true in the second one. And where I see true in the first one, I see false in the second one. If that's what we see, then the two statements are negations of each other. Think of it as they're exact opposites of each other. These two statements that are negations of each other are a really good example of something called DeMorgan's law. It's a way to take a statement and change it in a particular way to create the negation of that statement. So let's look for the pattern that we see here in these two statements that we know are negations of each other. The first simple statements are opposites. So I see P in the left one, I see not P in the right one. The second simple statements are also opposites. I see not Q in the first one, and I see Q in the second one. And one of those statements is a conjunction, an and the other is a disjunction. It's an or. That's the pattern that we can follow to write the negation of a conjunction or of a disjunction. So let's see how to do that with a statement that's in words. I ate dinner and I did not have any dessert. So we know that because we started with an and statement, a conjunction, the negation would have to be an or statement, a disjunction. We also have to negate each of the simple statements. So I ate dinner becomes I did not eat dinner. And I did not have any dessert becomes I did have dessert. So the truth values for our original statement, I ate dinner and did not have any dessert, are exactly the opposite of the truth values for I did not eat dinner or I did have dessert.